I'm going to talk to you today about instrumented protective systems specifically for use with distillation operations. I would like to acknowledge my co-author, Wayne Chastain, and he, I'm sure, will jump in at the end of the presentation to assist with any questions. So our typical continuous distillation system basically consists of 4 components: our distillation column, a condenser, a reflux pot, and a reboiler. And what we are trying to do here in general is separate 2 or more components based on their volatilities, where our low boiling component goes overhead to be condensed with energy removal in a condenser with some cooling media, and a portion of that condensed material would be returned to the column as reflux, and the other portion of that taken off as a product. And our high boiler would go into the base of the column, and we would supply energy for the boiling using a heating media in a reboiler. It's probably fairly familiar to most people that are in the room. And when we consider this distillation column, one thing we've got to be concerned about is what are the overpressure scenarios we might experience. Overpressure is defined as the accumulation of pressure inside our vessel or system above its rated or maximum allowable working pressure. We often abbreviate that as MAWP. The reason we're concerned about accumulated pressure is that it can lead to vessel failure and ultimately release of the contents. There are 16 overpressure scenarios that have been identified and should be evaluated for each vessel or system. And those 16 cases are further documented within API Standard 521. Now, fortunately, a subset of those 16 cases are the primary ones we're concerned with when we look at the distillation system. In general, overpressure scenarios in a distillation system are going to result from failures where we've got energy input at our reboiler that exceeds the energy removal capability of our condenser. In a steady state operation, the energy input and removal would be balanced, which would allow the column to operate at its normal operating conditions. However, we could get into an upset condition if we can no longer remove the energy that we are putting into the column. In order for an overpressure event to occur, we have to look at the vapor pressure of one of the components and determine if one or more of those components has a vapor pressure that's greater than our system rated pressure, or MAWP, at the temperature of the heating media. So we break down the 16 scenarios into approximately 5. And these are fairly standard, assuming our column is rated for full vacuum and we don't have to worry about vacuum relief. So we're focusing on overpressure. Liquid overfilling, which can also be called closed vessel outlet or vessel overfill, where we fill the column system with a liquid that has a supply pressure greater than the column rating. Also, this is where we would take into account static head of the liquid that fills the system. We also have a concern with loss of cooling, where we lose energy removal capability in the column system because we no longer have a functioning cooling system to the condenser. And we would continue to generate vapor in the base by adding heat through the reboiler. Abnormal heat input considers the maximum possible energy input into the column system through the heating media that's in the reboiler. In most cases, we would combine the evaluation for loss of cooling and abnormal heat input in that we may not take credit for condensing capability when we look at the maximum possible energy input into the base. So sometimes those cases are looked at in a kind of group together when we look at those. Split exchanger tube is a concern if we have a tube rupture that leads to introducing our heating or cooling media into the column system. And of course, we can have external fire impingement on the outside of the column, and that can lead to vaporization of the contents and subsequent overpressure. So here is our example column system. And as I go through, I'll probably refer back to the example column system in some slides. But in general, what we found here in the methodology we used for looking at instrumented protective systems could be applied to many other distillation systems using many other components. We had a system rated pressure of 75 psig. Our 2 components were acetone and water. And we are attempting to remove the acetone from the water stream due to environmental concerns. So we're going to take that acetone overhead and recover it, and then send the water stream to wastewater treatment. In order to do this, we needed to use 125 psig saturated steam, which had a supply temperature of 353 degrees Fahrenheit, and we used river water as our cooling media in the condenser. When we looked at the vapor pressure of the components, certainly water would have a vapor pressure above the system rated pressure, since it would be 125 psig, the same as our steam supply, but our acetone had a high vapor pressure compared to our system rated pressure of 268 psig. So we knew that an overpressure event due to abnormal heating or loss of cooling, or even split exchanger tube allowing steam to enter the system, could result in overpressure. We also had to consider the potential for an overpressure with gas or vapor from our nitrogen supply that we use for purging the system, as well as our external fire scenario. So we focused our evaluation of loss of cooling, abnormal heat input, and split exchanger tube on the steam supply to the reboiler. And we looked at an overhead vapor line relief device for overpressure with gas vapor from our nitrogen feed and our external fire scenario. When we determined that we needed to use an instrumented protective system in this case to provide protection for the column system, we looked at ASME Code Section 8, Division 1, UG 140, which does allow you to use an instrumented protective system to address an overpressure scenario. However, you do have several requirements that must be met in order to use your IPS to address that overpressure scenario. The vessel cannot be strictly an air, steam, or water service. The user is responsible for ensuring the vessel is appropriately protected, and that includes doing the risk assessment and the appropriate layers of protection analysis to determine that your protection is appropriate for what the needs of the column system are. The overpressure scenarios protected by system design must be announced so that operators can respond effectively and are aware that the situation is progressing. And of course, there are limitations on the maximum allowable pressure you can accumulate in the system. And the results of the analysis must be documented and signed. So what are the benefits of using an instrumented protective system to mitigate overpressure scenarios? In the first place, it will take the column system to a safe holding condition before it reaches the system rated pressure. So you may be able to minimize the impact of the overpressure event by stopping it early on as it precipitates. You can also block the flow of heating media to the reboiler, and that will stop vaporization in the system, but it can also help prevent the flow of high-pressure heating media into the column base due to a tube rupture. And that can provide protection for your column internals from a pressure surge if you get a tube break in the base and high-pressure heating media going up through the column. The relief system won't open if the set pressure is not reached, and that limits the impact of the scenario because you don't lose containment through the relief system. And you don't have to size an effluent handling system for the release through the relief system for that particular event. And ultimately, it could allow the relief designer to size the relief system for external fire case only. You cannot use your instrumented protective system to mitigate the external fire scenario because you can't count on that equipment surviving the impact of the external fire. And as I said, you can't use it for an external fire, but you can use it to address all credible overpressure scenarios for distillation systems with that exception. It must be independent of your basic process control system that is used to conduct the normal operation of the column system. And in this case, our concern in the BPCS is looking at not only the logic solver, but all instrumentation as well as field elements such as your control and your block valves. So in order to initiate our instrumented protective system, we must select a sensing device. Indicators are generally preferable to switches when we're choosing a sensing device because it's going to give us a way to monitor the operation of that sensing device and ensure that the failure of that sensing device would be revealed or announced. High base pressure is one that we typically use as an initiator because it is very directly associated with the overpressure event or the upset condition that could occur from heating media problems such as abnormal heat input or even loss of cooling as you continue to generate vapor in the column. High top pressure can be used, although care must be taken to ensure that pressure drop through the column is understood and that you're really getting an indirect measurement of problems in the base of the column when you initiate on high top pressure. However, if you have a plugging media or a tar or a sludge that is in the base of the column, high top pressure may be a safer way to initiate. High vent temperature could also be a reasonable initiator, but again, it's an indirect measurement of overpressure and overtemperature conditions in the base. High tray temperature can be very effective provided you can locate that tray temperature close enough to the base to get a very direct measurement of the overpressure condition. And the actions taken by the instrumented protective system, in general, we want to focus on closing the heating media supply to the reboiler and potentially closing the liquid feed if we're worried about a liquid overfill scenario. If you do have a high pressure vapor feed that can supply additional pressure to the column, that might also be something to consider closing on an overpressure event. So when we implemented an instrumented protective system on the example column, what we did was put in an interlock at the base to close the steam on high pressure in the base. And this allowed us to use that instrumented protective system to address loss of cooling, abnormal heat input, and split exchanger tube in the reboiler. And then we had an appropriately sized relief device that handled the other cases, overpressure with gas vapor and external fire. And we were able to use fire-resistant insulation to reduce the size of that relief system for the external fire scenario. So in order to determine what the reliability of the instrumented protective system needed to be, I performed a layers of protection analysis. And we've talked about this throughout the entire session. So we basically just looked at our single cause consequence events and looked at the frequency of occurrence and determined if the hazard could be adequately controlled by the instrumented protective system. So specifically talking about a LOPA on an overpressure scenario on a distillation column, the first thing we have to do is determine if the controls in place were adequate to prevent or mitigate the overpressure event. Since that wasn't the case, the LOPA indicated that some additional controls were needed other than the normal process control, and in this case the relief system, because I did not want to size the relief system for the magnitude of the event for abnormal heating or loss of cooling. And so we determined that some controls other than our adequately sized relief system could be used to address the hazard. And of course, we had to address all of the appropriate ASME code requirements for providing relief and overpressure protection for this column system. So the first LOPA I looked at was for loss of cooling. In this case, since it's an aqueous system, I looked at severe injury to personnel due to shrapnel from the vessel failing upon overpressure. My initiating failure was loss of cooling due to failure of my temperature control loop on the river water. I had a BPCS ESD that was in place in the DCS that could be tripped by high vent temperature and high base pressure. But I cannot take any credit for that because it was implemented in the same control system as my initiating failure, my temperature control loop. So looking at the likelihood of personnel in the area, the occupancy, and the likelihood of injury from a shrapnel event, I came up with a difference of -2.5. So I determined that I needed a SIL-2 interlock to close the block valve, and I would like to really close the block valve in the steam supply on high base pressure. And that would address my loss of cooling scenario. So then I moved on to look at abnormal heat input. A similar case, but my initiating failure here was a failure of the basic process control steam loop. And again, I could not take any credit for my BPCS interlock that would be tripped on high vent temperature and high base pressure. So in this scenario, I also determined I needed a SIL-2 interlock to close the block valve in the steam supply on high base pressure. So fortunately, both of those two scenarios were addressed by the same instrumented protective system. But then I had to look at the scenario of a tube rupture in the reboiler, which would have allowed steam at a higher pressure than the MAWP into the column. So a tube rupture in the reboiler is a less frequent event than the basic process control loop failure that I had previously evaluated, and I got to take credit this time for the interlock that was implemented in the BPCS. So in this scenario, I ended up with a difference of only -1. However, fortunately, the same interlock that I had planned for loss of cooling and abnormal heat input would also provide protection for the tube rupture scenario. So I was able to address 3 cases with a properly designed SIL-2 interlock installed to close off the steam supply. So in conclusion, when we look at these distillation systems, it's a very demanding unit operation from an overpressure protection viewpoint and a relief design viewpoint because there are large amounts of energy being exchanged. Traditionally, these systems have been protected by relief devices and relief systems. At first, we looked at using some inherently safer technology, such as rating the column system above the vapor pressure of the components at the steam temperature. However, due to the high vapor pressure of acetone in this case, that proved to be undesirable from a capital standpoint. So then we started looking at designing the relief system, and unfortunately, the reboiler needed to be very large because they were using potentially 15 psig steam as well in certain operating modes. So they designed a very large reboiler. So with the 125 psig steam, I had a very large heat input that I would have had to deal with, which made my relief system prohibitively large. So what we ended up doing before we looked at the LOPAs and looking at a SIL2 interlock, we tried to use a novel approach with a pressure relief system. And what we did was we considered the design of a relief device in the steam supply to limit the steam supply pressure to a manageable value. And the reason we did that is because they were going to use 15 psig steam in certain applications, and they were going to use 125 psig steam in certain applications. But they really only needed like 30 psig steam. So we put in a pressure reducing valve in the steam supply and created our own 30 psig steam supply and followed that up with a relief valve. So we put a large relief valve in the steam supply. And that also would have given us the same type of protection that our SIL2 interlock would have. So we looked at those various approaches, and those are written up in the paper as far as our thought process moving through. But we determined that the instrumented protective system could be effectively used on distillation systems, particularly to address certain relief cases, preventing us from having to relieve those and deal with the effluent handling situations, as well as minimizing the size of our relief system. So we did look at several approaches, but determined that the instrumented protective system would be very effective in this case. Are there any questions?